For decades, scientists believed the universe followed a clear set of rules. Then James Webb looked deeper than ever before and found galaxies, black holes, cosmic structures, and hidden forces that appear far too early, far too massive, and far too strange for the current model to explain. Every new discovery seems to widen the crack in what we thought we knew. Maybe the problem is not the data. Maybe the problem is our understanding of the universe itself. Today, we explore why James Webb may be revealing a different universe. Now, let's begin. A newborn retired before taking its first breath. That is the only way to describe what James Webb discovered when it locked its golden mirror onto a patch of sky 12 billion light-years away. The galaxy designated GS9209 had already lived a full life, formed hundreds of billions of stars, built a structure as massive as our own Milky Way, and then completely shut down. Dead, quiet, done. When the universe was just 1.8 billion years old. Let that land for a second. The universe today is 13.8 billion years old. The Milky Way itself took billions of years to assemble into what it is now. Every cosmology textbook, every simulation ever run, every equation physicists trusted for decades told us the same thing: galaxies are slow. They grow gradually, pulling in gas, igniting stars, spiraling into shape over vast stretches of cosmic time. You don't rush a galaxy? You can't. The physics won't allow it. And then GS9209 showed up and laughed at the physics. To understand the full weight of this discovery, you first need to understand what the standard model of cosmology actually promises. The framework called Lambda CDM, Lambda, cold dark matter, is not a rough sketch. It is the most rigorously tested, most precisely calibrated, most widely accepted model of cosmic structure ever constructed. It describes a universe that builds itself from the bottom up, patiently and methodically. First, quantum fluctuations from the Big Bang seed, the cosmos, with tiny variations in density regions that are barely, almost imperceptibly denser than the space around them. Dark matter, which does not emit light but does respond to gravity, slowly drifts into these regions over hundreds of millions of years. It forms vast invisible halos. Normal matter gas, mostly hydrogen and helium, falls into those halos. The gas cools. It collapses under its own gravity. Stars ignite. Clusters form. Small galaxies merge into larger ones. The whole magnificent architecture of the cosmic web assembles itself, piece by piece, over billions upon billions of years. Billions. That word is not decorative, it is structural. The timescale is not incidental to the model, it is the model. GS9209 did not have billions of years. It had 1.8 billion, and it used them to do something that, according to everything we thought we knew, was flatly impossible. The moment Webb's instruments resolved that signal infrared light that had spent 12 billion years crossing an expanding universe, finally pressing against 6.5 meters of gold-coated beryllium mirror, orbiting the Sun 1.5 million kilometers from Earth, something in the standard model quietly cracked. Not bent, not stretched under pressure. Cracked. Clean through. Here is what the data showed. GS9209 holds a stellar mass of approximately 800 billion solar masses, 800 billion times the mass of our Sun, locked inside a galaxy that had already gone completely silent. No new stars forming, no raw gas left to burn, no future being written anywhere inside it. The spectroscopic analysis of its starlight told the full story. The stellar population was old, cool, and uniformly aged, meaning they had all formed in a single intense burst, and then the galaxy had simply stopped. Astronomers confirmed the gas exhaustion through multiple spectral signatures. The fuel tank was empty. had been empty for a long time, even by the standards of a universe that was barely 1.8 billion years old. To understand why this is so deeply, structurally wrong, picture a construction site on its very first day. The land has just been cleared. No foundation has been poured. No steel has been delivered. No concrete. No framework. No scaffolding. Nothing but raw earth and the architectural plans for what will eventually become a building. You turn your back for 60 minutes. When you turn around again, there stands a completed 60-story skyscraper, fully furnished, every apartment occupied, and the residents are already collecting their retirement checks and complaining about the elevator being slow. That is JWST, a fully formed, fully exhausted cosmic skyscraper, standing on a construction site where the concrete wasn't even supposed to be dry yet. Astronomers at the University of Edinburgh who led the detailed spectroscopic study, published in 2023 in the journal Nature Astronomy, described JWST as one of the most massive quiescent galaxies ever confirmed at such an early cosmic epoch. Quiescent is the scientific word for a galaxy that has stopped forming stars. It sounds gentle. It is not. It means the entire productive life of this galaxy, its birth, its explosive growth, its slow decline, its death had already completed before the universe had lived through even 13% of its current age. To achieve a stellar mass of 800 billion solar masses in 1.8 billion years, JWST would have had to form stars at rates far beyond anything observed in the modern universe, sustain that pace without interruption, and then abruptly shut everything down through some mechanism powerful enough to expel or destroy every remaining trace of star-forming gas. Some theorists point to an extraordinarily active supermassive black hole at the galaxy's center, generating feedback energy so violent it blew the remaining gas clean out of the system, effectively suffocating the galaxy's own future. Others suggest star formation efficiencies that push well past the theoretical upper limits currently built into our simulations. Every single proposed explanation requires invoking a physical process working faster, harder, and more ruthlessly than anything our current models permit. So here's the question worth sitting with. What could possibly build a galaxy 800 billion times the mass of the Sun in just 1.8 billion years? The honest answer from the scientific community is we do not know. And that phrase coming from the people who mapped the cosmic microwave background to 5 decimal places and predicted the mass of the Higgs boson before it was detected carries enormous weight. Theoretical physicists looked at JWST with the exact same expression a professor makes when a student submits a perfect, fully completed final exam before the exam paper has even been handed out. It is not just impressive, it is suspicious. It violates the established sequence of events. And in science, when something violates the sequence that the laws of physics are supposed to enforce, one of two things is true. Either the measurement is wrong, or the laws are incomplete. Webb made no measurement error. The data was cross-confirmed across multiple instruments aboard the telescope, independently verified by separate research teams, and validated across multiple wavelengths of light. JWST is real. Its distance is real. Its mass is real. Its silence is real. The universe constructed something it had no right to construct. At a time, it had no business building anything that large, and then went completely quiet before the rest of creation had even figured out how to assemble its first star cluster. And the worst part? JWST was only the beginning. A few weeks after that discovery, Webb sent back images of not one but hundreds of galaxies exactly like it. And that is when scientists really started to worry. You cannot build a house without bricks. This is not a preference. It is not a design philosophy. It is a hard physical constraint so fundamental that no architect, no engineer, no creative workaround can dissolve it. The material must exist before the structure can. The supply comes before the product, always, without exception. The early universe had a fixed, finite, calculable supply of bricks. In the immediate aftermath of the Big Bang, the cosmos was filled with a specific, measurable quantity of matter, overwhelmingly hydrogen and helium, distributed across space with near-perfect uniformity. The slight deviations from that uniformity, imprinted by quantum fluctuations during the first fractions of a second, are the seeds from which all cosmic structure eventually grew. Gravity worked on those seeds slowly. Over hundreds of millions of years, matter began drifting toward the denser regions. Dark matter halos assembled, gas fell in, stars began to form. And the rate at which all of this happened, the tempo of cosmic construction, was constrained not just by the amount of matter available, but by the fundamental speed at which gravity could gather it. At 500 million years into cosmic history, gravity simply had not had long enough to concentrate sufficient raw material into any single region to produce the kind of galaxies Webb was now revealing. This is not a philosophical statement. It is a mathematical one, derived from the known density of matter at the time of the Big Bang, the known rate of cosmic expansion, and the known behavior of gravitational collapse. The numbers are firm, the timeline is firm, and the galaxies Webb found broke both. This is what cosmologists now call the stellar mass problem. And it is one of the most serious unresolved crises in modern physics. The world's most sophisticated simulations of cosmic evolution, illustrious TNG, developed by a multinational collaboration running on supercomputers processing millions of CPU hours, and Eagle, the evolution and assembly of galaxies and their environments simulation, developed by European research teams, are not simplistic models. They encode the known laws of physics at extraordinary resolution: gravitational dynamics, gas, thermodynamics, dark matter clustering, radiation pressure, stellar feedback, supernova-driven outflows. These simulations represent the cumulative product of decades of theoretical refinement and computational power. They are the best predictions modern cosmology can produce. Webb looked at the universe at 500 million years old and found between 10 and 100 times more stellar mass than every single one of those simulations predicted was possible. Read that again. Not 10% more, not twice as much, 10 to 100 times the stellar mass that the combined predictive power of every simulation humanity has ever built said should be there. In November of 2022, a team led by astronomer Ivo Labbé at Swinburne University of Technology published a paper in the journal Nature that sent a very specific kind of controlled panic through the cosmological community. Analyzing Webb's early deep field imaging data, they identified 6 massive galaxy candidates at redshifts, placing them between 500 million and 700 million years after the Big Bang. These objects were so luminous, so apparently massive, and so unexpectedly numerous that if their distances and stellar masses were confirmed, they would represent what Labbé and colleagues carefully, deliberately described as galaxies that should not exist within the standard cosmological framework. One candidate alone appeared to hold a stellar mass approaching 100 billion solar masses. Another approached the mass of our entire modern Milky Way, all of them fully assembled, fully massive, sitting in a universe that was cosmologically speaking barely out of diapers. Think of it this way. Your city has been allocated an annual construction budget sufficient to build exactly 10 houses. That is the total available material. That is the total available workforce. That is the hard ceiling set by every logistical constraint in the system. You go to sleep on Sunday night, Monday morning. You step outside and find 100 fully built, fully furnished, fully occupied houses lining your street. Not under construction, complete, and nobody, not the city council, not the construction crews, not the materials suppliers can account for where the extra 90 came from, you would not conclude that someone miscounted the budget. You would conclude that something is fundamentally broken in your understanding of how houses get built. That is exactly where cosmologists found themselves in late 2022 and through all of 2023. Some researchers initially maintained legitimate scientific skepticism. Distance estimates at extreme redshifts carry uncertainties. Gravitational lensing can magnify background objects and inflate apparent brightness. Stellar population models used to convert observed light into mass estimates involve assumptions that could, in principle, be wrong. These were real possibilities, seriously entertained, methodically tested. They did not solve the problem. Follow-up spectroscopic observations, which provide far more precise distance and mass measurements than photometry alone, confirmed multiple of these candidates as genuine massive galaxies at the distances initially estimated. Cross-verification came from near-infrared and mid-infrared photometry. Independent teams using different analysis pipelines and observations from ground-based facilities supplementing Webb's space-based data. By 2023, the mass excess was not shrinking under scrutiny. It was solidifying. The candidates were real. The masses were real. The timestamps were real. And the gap between what the simulations predicted and what the universe had actually produced was not closing, it was widening. The excess is not noise. It is not calibration drift. It is not a systematic artifact waiting to be calibrated away. It is the universe presenting its ledger and showing numbers that do not balance against any known physical accounting. And if you ask the logical follow-up question, if there was not enough matter available to produce what we are observing, then where did that matter come from? The answer is worse than "we don't know." The answer is that the question itself may be pointing toward a flaw in something far more foundational than any individual measurement. The way gravity gathered matter in the early universe, the nature of dark matter, and how efficiently it clustered. The initial spectrum of density fluctuations seeded by inflation. Any one of these, or some combination of all of them, may need to be revised at a level that rewrites not a chapter of cosmology, but the entire first volume. The situation is exactly like ordering pizza for 5 people, opening the delivery box, and finding enough slices to feed 50 with no record of who placed the extra order, no explanation for how it fit in the same box, and no delivery driver who admits to making a second trip. Now, if you think the problem is only in what Webb sees, wait until we get to what Webb measured, because this telescope just confirmed that space itself is expanding in a way that no one can explain. The Hubble constant is the heartbeat of cosmology. Every serious calculation about the universe, its age, its size, its fate, the distance to any galaxy beyond our local neighborhood, runs through this single number. It tells us how fast space itself is stretching for every megaparsec of distance between 2 points in the cosmos. Those points are flying apart at a specific velocity measured in kilometers per second. Get this number right, and the entire architecture of modern cosmology holds together. Get it wrong, and every structure built on top of it becomes suspect. Which is exactly why what James Webb confirmed about the Hubble constant is not a minor technical disagreement between specialists. It is a crisis, a real one, and it has been building for years. There are 2 primary ways to measure how fast the universe is expanding, and they approach the problem from completely opposite directions in time. The first method looks backward as far as physically possible, all the way to the cosmic microwave background. The faint afterglow of radiation released roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen for the first time. This radiation fills the entire sky at a temperature of just 2.7 Kelvin, barely above absolute zero, and its tiny temperature fluctuations encode an extraordinary amount of information about the early universe. The Planck satellite mapped these fluctuations to extraordinary precision, and from that map, cosmologists derived a Hubble constant of 67.4 kilometers per second per megaparsec. This is the universe's expansion rate as written into its very first light. The second method looks at the nearby universe using a different ruler entirely. Type Ia supernovae, the thermonuclear explosions of white dwarf stars that always detonate at nearly the same intrinsic brightness. Because their true luminosity is known, astronomers can calculate their distance from how bright they appear in the sky. And by measuring how fast the galaxies hosting those supernovae are receding from us, they derive an independent measurement of the expansion rate. This method, refined over decades and anchored by observations of Cepheid variable stars as intermediate distance rungs on what astronomers call the cosmic distance ladder, consistently produces a Hubble constant of approximately 73 kilometers per second per megaparsec, 67.4 versus 73, a difference of roughly 9%. 9% sounds modest, but apply that discrepancy to the full 13.8 billion year age of the universe. And you are talking about an error in cosmic timing that stretches across more than 1 billion years. The universe, depending on which measurement you trust, is either older or younger than we think by a margin, larger than the entire history of complex animal life on Earth. That is not a rounding error. That is not measurement noise. That is a chasm. For years, physicists on both sides of the debate hoped that the answer lay in systematic errors, subtle biases baked into the instruments or the analysis methods that, once identified and corrected, would make the two numbers converge. Cepheid variable stars, used as distance calibrators in the local measurement, were the most frequently cited source of potential error. Their brightness pulsations are used to determine distance, but crowded stellar fields and dust can contaminate those measurements. If the Cepheid distances were slightly off, maybe the local expansion rate was slightly off too. Maybe the two numbers would eventually shake hands. Webb was supposed to settle it, with its infrared sensitivity and resolution far surpassing anything before it. Webb could observe Cepheid stars in distant galaxies with a clarity that ground-based telescopes and even Hubble simply could not match. It could see through dust. It could resolve individual stars in crowded fields. It could eliminate, one by one, every systematic uncertainty that had kept the debate alive. And did eliminate them, every single one. In 2023, the team led by Nobel laureate Adam Rees published results from Webb's Cepheid observations, confirming with higher precision than ever before that the local expansion rate is real, robust, and solidly near 73 kilometers per second per megaparsec. The systematic errors were not the answer. The contamination was not the answer. The Cepheid measurements were sound. Webb did not resolve the Hubble tension. It made it irreversible. Imagine the two most precise atomic clocks ever constructed, clocks accurate to within 1 second over the entire age of the universe, built by different teams using different technologies, placed side by side in the same room, set to measure the same morning. You look at them at noon. One reads 12:00, the other reads 12:09. You recalibrate both. You check every gear, every oscillator, every power source. You find no faults. You run them again. They still disagree by 9 minutes. At that point, the question is no longer whether one of the clocks is broken. The question is whether time itself is behaving differently for each one, and why. That is the position cosmology is now in. The statistical significance of the Hubble tension, as of the most recent combined analyses, stands at approximately 5 sigma. In particle physics, 5 sigma is the threshold for declaring an official discovery the point at which the probability of the discrepancy arising from random chance falls below 1 in 3.5 million. This is the same bar that had to be cleared before the Higgs boson was announced as a confirmed detection in 2012. The Hubble tension has now cleared it. This is not a hint of a problem. This is a confirmed, statistically bulletproof disagreement between two valid measurements of the same physical quantity. Something is different between the early universe and the late universe. Either there is new physics operating in the first few 100,000 years of cosmic history that altered the expansion rate before the cosmic microwave background was imprinted some early dark energy, some exotic particle, some phase transition that the standard model does not include, or there is new physics in the nearby universe, something affecting how light from supernovae and Cepheids travels to us, or how the local cosmic web influences our measurements. Both options require something outside the known rulebook. There is no version of this resolution that leaves the standard model intact. So here is the question that deserves a moment of honest reflection. A 9% discrepancy in the expansion rate, when scaled across the 13.8 billion year life of the universe, represents a timing error of over 1 billion years. How much of what we think we know about cosmic history is built on a clock that may be running at the wrong speed? Cosmologists working on this problem today are in the exact position of a GPS engineer whose own navigation system is pointing to two different locations for the same coordinate, and both readings check out as accurate. The equipment is not broken. The satellite signals are clean. The math is correct. And yet the map says you are in two places at once. The only rational conclusion is that something about the territory itself, space, time, or the physics connecting them is not behaving the way the map was drawn to represent. If the universe is expanding at a rate no one can pin down with certainty, then we also don't fully know how it began. And Webb just looked at the skeleton of the universe, dark matter, and found that it, too, is behaving completely wrong. Picture the largest structure you can hold in your mind. Not a building, not a city, not a continent. A web vast beyond any scale human intuition was built to process stretching across hundreds of millions of light years in every direction. Its filaments made not of steel or stone, but of dark matter, the invisible gravitational scaffolding upon which every galaxy, every cluster, every thread of luminous cosmic structure is draped like morning dew on a spider's silk. Astronomers call it the cosmic web, and it is, in the most literal physical sense, the skeleton of everything that exists. Without the cosmic web, there are no galaxies. Without dark matter halos anchoring the web's nodes, there are no stars. Without the filaments channeling gas along their lengths toward the dense intersection points, there is no raw material for any of the cosmic architecture Webb has been photographing in such devastating detail. The web is not decorative, it is foundational. It came first, and the entire standard model of cosmology is built around a very specific prediction about how long it took to form. The prediction is this: the cosmic web assembled itself slowly, hierarchically, from the bottom up. Tiny dark matter halos formed first, collapsed under their own gravity, then merged with neighboring halos, growing larger over time. Small proto-galactic clumps came before larger ones. The first protoclusters, the massive intersection nodes where dozens of galaxies would eventually congregate, required billions of years of merging and accretion before they achieved the scale and organization needed to be recognizable as true large-scale structure. The math behind this prediction is not arbitrary. It comes directly from the known amplitude of primordial density fluctuations, imprinted at the moment of inflation and read with exquisite precision from the cosmic microwave background. The fluctuations were small. The growth had to be slow. Webb looked at the universe at 650 million to 800 million years old and found protoclusters that had no business being there. not hints of protoclusters, not marginal candidates requiring generous interpretation. Confirmed, spectroscopically verified overdensities regions where dozens of massive galaxies had already gathered around what must have been extraordinarily large dark matter halos, organized into coherent large-scale structure at a cosmic age when the standard model predicts the universe should still be assembling its first modest galactic building blocks. One confirmed protocluster system, observed at a redshift, placing it at roughly 650 million years after the Big Bang, contained multiple massive galaxies clustered together in a configuration that implied an underlying dark matter halo of staggering scale, far exceeding what the known amplitude of primordial density fluctuations could have produced in that time frame. This is where the numbers become genuinely disturbing. The mass of the dark matter halo needed to gravitationally organize a protocluster of that size. At that epoch, requires density fluctuations in the early universe that are orders of magnitude larger than what quantum mechanics and inflationary theory together permit. The primordial fluctuations are not a free parameter. They are directly measured in the cosmic microwave background. They have a known amplitude, and that amplitude, by the well-established mathematics of gravitational collapse, sets an absolute ceiling on how quickly dark matter can cluster into structures of a given mass. The protoclusters Webb is finding are breaking through that ceiling. Think of it this way. You are a historian studying the development of American cities, and you have access to every census record, every land survey, every population map going back to the founding of the Republic. Based on all of that evidence, you build a rigorous model of how cities grow settlements, become villages, villages become towns, towns become cities, cities become metropolises. The process takes generations, follows predictable patterns, leaves identifiable archaeological traces at every stage. Then someone shows you a photograph of a fully functioning city of 10 million people, complete with skyscrapers, subway systems, and an international airport, sitting on land that your records show was uninhabited wilderness just 200 years ago. No village stage, no town stage, no gradual urban evolution, just wilderness. And then a global metropolis. Your model does not have a category for this, because your model says it cannot happen. That is what Webb found in the early universe. Not the expected sequence of gradual hierarchical assembly, mature, organized, large-scale structure where the mathematics of dark matter clustering says there should be almost nothing. The implications point towards something the standard cold dark matter model was specifically designed not to require some form of interaction or behavior among dark matter particles that allows them to cluster more efficiently, more quickly, and at larger scales than the standard purely gravitational picture permits. Two theoretical frameworks that were largely considered exotic or speculative until recently are now receiving serious renewed attention. The first is fuzzy dark matter, a model in which dark matter consists of ultralight particles with a mass around 10 to the power of -22 electron volts, so light that their quantum wave nature becomes relevant on galactic scales. These particles form coherent quantum states that suppress structure formation on small scales, but may allow more efficient large-scale clustering under certain conditions, potentially helping explain the overabundance of early massive structures. The second is self-interacting dark matter, or SIDM, a model in which dark matter particles interact with each other through some force beyond gravity, allowing them to exchange momentum, redistribute within halos, and cluster in ways that cold, collisionless dark matter cannot. SIDM has long been considered a solution to discrepancies in the internal structure of dwarf galaxies. Webb's early structure observations are now giving it a larger stage to perform on. Neither model is confirmed. Both are now being taken considerably more seriously than they were 3 years ago. Consider what this means for the big picture. Dark matter constitutes 27% of the total energy content of the universe. It is the dominant gravitational influence on every scale above individual stars. If dark matter behaves even slightly differently from the cold, collisionless, purely gravitational particle, the standard model assumes if it has even a modest self-interaction, or if its particle mass lands it in a quantum regime with observable consequences, then every simulation, every prediction, every carefully tuned model of cosmic structure formation needs to be rebuilt from a different foundation. Here's the question that cuts to the bone. If dark matter, the invisible substance that makes up 27% of the entire universe, is not behaving the way we think it is, then how much of our cosmic map was drawn from the wrong blueprint? Dark matter is, in the most ironic possible sense, the hardest working component of the universe. It does not emit light. It does not emit heat. It does not interact with any of the forces we can directly measure, except gravity. It shows up, does its gravitational duty in complete silence, and asks for nothing in return. And yet, it is now the one thing in the entire cosmos that is refusing to follow the rules everyone wrote for it. Dark matter is behaving wrong. The expansion rate is wrong. The stellar mass is wrong. The galaxy ages are wrong. But we still haven't reached the thing that keeps physicists awake at 3 in the morning, the mysterious repulsive force that is dictating the fate of the entire universe. 68% of the universe is dark energy. We have no idea what it actually is. But the situation just became considerably worse because we just discovered it may be changing. Sit with that for a moment. Not the mystery of what dark energy is. That mystery has existed since 1998, when 2 independent teams studying type Ia supernovae discovered, to their collective astonishment, that the universe's expansion is not slowing down under gravity as expected, it is accelerating. Something is pushing space apart, and it is getting more powerful over time, or at least it was assumed to be doing so at a constant rate. That discovery won the Nobel Prize in Physics in 2011. Since then, dark energy has been the single largest component of the universe by energy content, the dominant force shaping the cosmic future, and simultaneously the most profound unsolved problem in all of physics. For over 2 decades, the standard treatment of dark energy rested on a single symbol inside Einstein's field equations, lambda. The cosmological constant, originally introduced by Einstein in 1917 as a term to keep the universe static and famously abandoned by him after Hubble's discovery of cosmic expansion, lambda was resurrected in a new role after 1998 as the mathematical representation of dark energy. In this framework, lambda is fixed, immutable, a property of space itself, uniform across all of cosmic history, carrying the same energy density whether the universe is 1 billion or 100 billion years old. It does not evolve. It does not fluctuate. It is simply there, built into the geometry of space-time like a permanent architectural feature, driving acceleration at a perfectly steady rate from the first moment it became dominant to the last moment of cosmic time. That assumption just cracked. In 2024, the Dark Energy Spectroscopic Instrument DSA released the results of its first year of full survey operations, mapping the 3-dimensional positions of approximately 6 million galaxies and quasars across a broad sweep of cosmic history. The analysis focused on baryon acoustic oscillations, the regular spacing of galaxy clustering that acts as a standard ruler across cosmic scales. And when DSE used that ruler to trace how the expansion rate has evolved over billions of years, the data pointed towards something the lambda model cannot accommodate: dark energy that is not constant. Its strength appears to have varied over cosmic time. The key parameter here is W, the equation of state of dark energy, which describes the relationship between its pressure and its energy density. In the standard lambda model, W equals precisely -1. Always, everywhere, at every moment in cosmic history. That specific value of -1 is what makes dark energy behave as a cosmological constant, a fixed background energy woven into the fabric of space. Think of it like the climate control system in a perfectly sealed room. If W equals -1, the thermostat is locked. The temperature never changes. You cannot override it. You cannot feel it fluctuating. You can only measure its constant, unwavering output. The room is always exactly the same temperature, today and a billion years from now. But if W does not equal -1, if it drifts above or below that value, the thermostat is alive. It is adjusting. The room is getting warmer or colder, and you cannot find the remote to stop it. You are not in a sealed, controlled environment anymore. You are in a system that is evolving, with consequences you cannot calculate from first principles because you do not know the rule governing how it changes. DESI's 2024 results, when analyzed across their full redshift range, showed W deviating from -1 at a statistical significance approaching 3 sigma, with the combined data set incorporating earlier Galaxy survey data from BOSS and eBOSS alongside DESI's new measurements, pushing the significance higher. When those results were cross-referenced with independent constraints from Webb's high redshift galaxy observations, the picture that emerged was of a dark energy that was behaving more like a dynamic field than a fixed constant, not dramatically, not obviously, but measurably, persistently, across multiple independent datasets pointing in the same direction. The theoretical framework that describes this possibility has a name: quintessence. It posits that dark energy is not a fixed property of spacetime, but rather a scalar field, a dynamic energy field that permeates the universe and evolves over time, like a cosmic tide with its own slow rhythm, rising and falling across billions of years according to internal dynamics that depend on the specific shape of its potential energy curve. Quintessence was proposed in the late 1990s, explored seriously for a period, and then largely set aside when the observational data available at the time was too imprecise to distinguish it from a simple cosmological constant. It was not disproven. It was just deprioritized. It is being taken very seriously again now. The catastrophic implication of a varying dark energy is not merely theoretical. Every scenario ever constructed for the ultimate fate of the universe, the Big Freeze, in which the cosmos expands forever into cold darkness as all stars burn out and all structure dissolves. The Big Rip, in which an ever-strengthening dark energy eventually tears apart galaxies, then solar systems, then planets, then atoms themselves. The Big Crunch, in which dark energy somehow reverses and gravity eventually pulls everything back together. Every single one of these scenarios is built on specific assumptions about the long-term behavior of W. If W is not constant, if it is slowly drifting across cosmic time along some trajectory we do not yet understand, then all of those end-state predictions are not merely uncertain. They are, in the most precise scientific sense of the word, void. We have been writing the epilogue of a story whose final chapters we have not actually read. There is a direct connection here to the Hubble tension discussed in the previous part. One of the leading theoretical proposals for explaining the 9% discrepancy between early universe and late universe expansion measurements involves a form of dark energy that was stronger in the first few 100,000 years of cosmic history, so-called early dark energy, before settling toward its current value. If dark energy evolves, it could have altered the expansion rate during the epoch when the cosmic microwave background was formed, shifting the early universe measurement of the Hubble constant upward toward the local value. The same variable dark energy that DSE is now hinting at in the late universe may be the key that unlocks the crisis that Webb made irreversible. a single evolving field potentially connecting two otherwise separate catastrophes in the Standard Model. If the repulsive force driving cosmic acceleration is genuinely increasing, and the Big Rip scenario becomes more plausible, the sequence of destruction is clinically precise. First, in tens of billions of years, dark energy overwhelms gravity and tears galaxy clusters apart. Then individual galaxies dissolve, then solar systems. Then, in the final moments, the force between protons and neutrons inside atomic nuclei becomes insufficient to hold against the expansion of space, pressing inward at subatomic scales. The atoms themselves are shredded. The last structures in the universe are not stars or planets, or even molecules. They are elementary particles, drifting in an infinitely cold, infinitely empty, infinitely expanding void. And now the question that earns its weight: if the repulsive force is genuinely increasing, if the universe is accelerating its own expansion at a rate that has not yet stabilized, what happens when it grows strong enough to tear apart not just galaxies, but the very atoms that make up everything, including you? Discovering that dark energy might be changing is exactly like driving on a highway, where the traffic laws have always been fixed and reliable: same speed limit on every sign, same rules at every exit, and then gradually noticing, over the course of a long journey, that the speed limit signs are reading different numbers than they did an hour ago. Not because you misread them, not because the signs are damaged, but because the legal speed limit itself is quietly, autonomously rewriting itself while you drive. You are still on the same road, but the road is no longer operating under the rules you started with. We just watched every pillar of cosmology tremble. But what comes next will reveal that what Webb found does not only break the equations, it is breaking the shape of space itself. The cosmological principle is not a law derived from observation. It is an assumption, a starting axiom baked into the foundation of every equation, every simulation, every prediction that modern cosmology has ever produced. It states that the universe, when viewed at sufficiently large scales, is homogeneous, the same in every location, and isotropic, the same in every direction. No region is special. No direction is preferred. Zoom out far enough, and the cosmos becomes a smooth, featureless sea of evenly distributed matter and energy. This assumption is not decorative. Remove it, and the entire mathematical framework of cosmology, the Friedmann-Lemaitre-Robertson-Walker metric, the equations governing cosmic expansion, the models predicting the large-scale distribution of galaxies, collapses into unsolvable complexity. The cosmological principle is what makes the universe mathematically tractable. It is the reason physicists can write down equations that describe the behavior of the entire cosmos from a single vantage point. It has been accepted not because it was rigorously proven true, but because for decades the observational evidence seemed consistent with it, and without it, the math becomes unworkable. The universe, apparently, was not consulted before this assumption was made. The Hercules Corona Borealis Great Wall is the largest known structure in the observable universe, discovered through the spatial distribution of gamma-ray bursts and confirmed through subsequent analyses. It stretches approximately 10 billion light-years in its longest dimension. 10 billion light-years. The entire observable universe, the full sphere of space, from which light has had time to reach us across 13.8 billion years of cosmic history, spans approximately 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall occupies roughly 1/9 of that total diameter in a single continuous structure. That number needs to sit uncontested for a moment before moving on. According to inflationary cosmology, the theory describing the explosive exponential expansion of the universe in its first tiny fraction of a second, which is itself one of the best supported frameworks in all of modern physics. The universe should become statistically homogeneous at scales above approximately 1.2 billion light-years. Above that threshold, the density variations that seed structure formation should average out. No coherent structure, no filament, no wall, no void should maintain organizational integrity at scales larger than roughly 1.2 billion light-years. This is not a preference built into inflation arbitrarily. It is a direct mathematical consequence of the spectrum of quantum fluctuations that inflation produces, a spectrum measured with extraordinary precision in the cosmic microwave background. The Hercules Corona Borealis Great Wall is more than 8 times larger than that theoretical maximum, 8 times the scale at which the universe is supposed to have smoothed itself out. A structure so vast that light traveling at 300,000 kilometers per second would require 10 billion years just to cross it, meaning this structure is older than the time it would take light to traverse it, which creates its own set of deeply uncomfortable questions about how it assembled in the first place. The violation does not stop at size. Studies using Planck satellite data and subsequent analyses incorporating Webb observations have identified what researchers call the axis of evil, a term coined, with appropriate dramatic weight, for the anomalous alignment of low multipole moments in the cosmic microwave background that suggests the universe has a preferred direction at the largest observable scales. Galaxy spin axes, quasar polarization vectors, and large-scale filament orientations have all shown statistically significant alignments that should not exist in a truly isotropic universe. A 2022 analysis of over 170,000 galaxies from the KDS survey found handedness in galaxy spiral orientations that varied systematically across the sky. A universe with no preferred direction should show no such pattern. It does. This matters at a level deeper than the discovery of any single anomalous structure. The SLRW metric. The mathematical backbone of standard cosmology is derived entirely from the assumption that the cosmological principle holds. Every calculation of the Hubble constant, every model of dark energy evolution, every prediction about the large-scale geometry of space-time is built on equations that assume perfect homogeneity and isotropy at large scales. If those assumptions are only approximate, if the real universe has genuine, large-scale inhomogeneities, preferred directions, and structures that violate the theoretical smoothness threshold, then those equations are not exact descriptions of reality. They are rough approximations whose errors compound across cosmic scales and billions of years of evolutionary history. Some researchers have begun exploring whether certain persistent cosmological anomalies, including aspects of the Hubble tension itself, might be partially explained not by new fundamental physics, but by a genuine large-scale inhomogeneity in the universe's matter distribution that biases our local measurements of expansion. If we happen to live in a region of the cosmos that is slightly underdense compared to the cosmic average, a possibility some data hints at our local measurements of the expansion rate would appear systematically higher than the true global value, generating exactly the kind of discrepancy we observe. This does not eliminate the need for new physics, but it suggests the problem may run deeper than any single missing particle or field. So here is the question that follows naturally: if the cosmic map has genuinely special regions, places where the rules of large-scale structure have been broken, where matter organized itself into structures that should not exist, where the universe has an apparent grain or directionality, what does that imply about the significance of where we find ourselves within it? The cosmological principle is essentially science's way of saying the universe is fair. No location is more special than any other, no direction more significant, no address in the cosmos carrying more weight than the one next door. And the universe has responded to that principle by constructing a 10 billion light-year wall, aligning galaxies along preferred axes, and generating structures that are 8 times larger than the maximum size inflationary theory says should be possible. as if it heard the assumption and decided, with some cosmic indifference, to make it demonstrably wrong. The universe is not uniform in space. But what about in time? The records of the very first stars have just been decoded by Webb, and they should not exist under any scenario we currently have. The Big Bang made 3 elements: hydrogen, helium, and trace amounts of lithium. That is the complete inventory of matter that emerged from the first few minutes of cosmic history, a universe of almost perfect chemical simplicity. Vast and hot, and utterly without complexity. Every other element in existence, from the carbon in your cells, to the oxygen in your lungs, to the iron in your blood, was forged later, inside the nuclear furnaces at the cores of stars, and scattered across space when those stars died. This is one of the most beautiful and well-confirmed stories in all of science. Carl Sagan called us star stuff. He was being precise, not poetic. The process takes time, significant time. A star must be born, spend millions to billions of years fusing lighter elements into heavier ones, and then die either in a supernova explosion that scatters those elements across surrounding space or through slower mass loss in its final stages. The next generation of stars forms from that enriched gas. They live, they die, they enrich the gas further. Over multiple generations, the heavy element content of the interstellar medium builds up gradually, generation by generation, in what astronomers call chemical evolution. It is a slow, patient, multi-generational process. The universe does not manufacture a full periodic table overnight. Webb looked at galaxies 400 million to 600 million years after the Big Bang and found carbon, oxygen, and silicon already present in measurable, significant abundances. Carbon, oxygen, silicon, elements that require stellar nucleosynthesis, the actual fusion of lighter nuclei inside stellar cores, operating under pressures of hundreds of billions of atmospheres, and then the violent dispersal of those elements back into the interstellar medium through stellar death, to arrive at detectable abundances of carbon and oxygen in galaxies at 400 million to 600 million years after the Big Bang. The universe would have needed to complete at minimum 2 to 3 full generations of population 3 stars, the hypothetical first generation of stars, formed from pure hydrogen and helium, including their full lifespans and their deaths. All packed into a time frame the physics of star formation does not accommodate. Population the 3 stars are themselves one of the most important unsolved problems Webb was specifically designed to address. Theory predicts they should have existed in enormous numbers in the first few 100 million years of cosmic history, massive, hot, short-lived behemoths burning through their hydrogen at ferocious rates, living fast and dying in spectacular explosions that seeded the early universe with the first batch of heavy elements. They are the universe's first chemists. Every model of early cosmic evolution requires them. And Webb, despite staring into the epoch where they should be most abundant, has not directly detected a confirmed population 3 star or star cluster. Their chemical fingerprints show up in the abundance patterns of subsequent galaxies. But the stars themselves remain invisible, present in the data's implications, absent from its direct observations. This disappearing act creates a paradox with 2 uncomfortable horns. Either population 3 stars existed and produced the heavy elements we observe, but are somehow too faint or too short-lived for even Webb to catch at these distances, which requires them to have formed and died with extraordinary efficiency in a window of time too narrow for current models to explain, or the heavy element abundances Webb is measuring reflect a chemical enrichment process faster and more efficient than any stellar evolution model currently predicts. Neither resolution is comfortable. Then comes UHZ1. In 2023, a joint analysis combining Webb observations with X-ray data from the Chandra Space Telescope confirmed the existence of a supermassive black hole at a redshift, placing it 470 million years after the Big Bang. UHZ-1. The designation given to this object harbors a black hole with an estimated mass between 10 million and 100 million times the mass of our Sun. Assembled, somehow, in less than 500 million years from a starting point of essentially nothing. Standard black hole formation theory is unambiguous about how supermassive black holes are supposed to grow. A massive star at minimum tens of solar masses lives its life, exhausts its nuclear fuel, and collapses in a supernova. The remnant core becomes a stellar mass black hole of perhaps 10 to 100 solar masses. From there, the black hole grows by accreting surrounding gas and merging with other black holes, a process limited by the Eddington luminosity, the physical ceiling on how fast a black hole can accrete before radiation pressure from its own feeding pushes the infalling gas away. Even growing at the maximum, theoretically permitted rate continuously from birth, a stellar mass black hole cannot reach tens of millions of solar masses in 470 million years. The math simply does not close. The proposed escape route is a mechanism called direct collapse. Under specific conditions in the very early universe regions, where molecular hydrogen cooling is suppressed by intense radiation fields from neighboring galaxies, preventing the gas from fragmenting into stars, a massive cloud of primordial gas might bypass the stellar stage entirely. Instead of breaking apart into individual stars that live and die over millions of years, the entire cloud collapses directly into a single, massive object, a direct collapse black hole, potentially with an initial mass of 10,000 to 100,000 solar masses. Starting from that far larger seed, reaching the mass of UHZ-1 within the available time becomes mathematically possible, though still barely, and only under the most generous accretion assumptions. Direct collapse has been theorized for years. It has never been directly observed or confirmed. UHZ-1 is the most compelling observational case yet made for its existence. But it remains an inference from mass and timing, rather than a witnessed event. The mechanism requires specific environmental conditions that may or may not have been common in the early universe. And if direct collapse was widespread enough to produce the number of supermassive black holes Webb is finding at extreme redshifts, it implies a population of very massive black hole seeds that itself demands explanation seeds too large to have formed through any well-understood process. Think of discovering a 500-year-old oak tree standing in the middle of a forest that was bare ground just 50 years ago. Not a sapling, not a young tree, a fully mature, centuries-old giant with no root system connecting it to any identifiable seed source, in soil that was documented empty within living memory. You would not conclude that oak trees grow faster than you thought. You would conclude that something about this tree's history is missing from the record entirely, that there is a chapter of its existence that no one witnessed and no current model accounts for. These early black holes skipped the entire standard curriculum of black hole formation. No stellar life, no supernova, no gradual accretion from a small seed, and instead collapsed directly to their final professional title. Like a new hire who bypasses every entry-level position and shows up on their first day already sitting in the CEO's chair. With decades of institutional authority and no resume anyone can verify. Stars wrong, black holes wrong, elements wrong, and now we cannot avoid the question that has been building since the very first data came back from Webb. If every single piece of observational evidence contradicts the model, is it possible that the model itself is what's broken? Lambda CDM was supposed to be the theory of everything for the universe. Not in the particle physics sense, not a unified theory of all fundamental forces, but in the cosmological sense, a single coherent framework that could explain how the universe evolved from a hot, dense, nearly uniform state immediately after the Big Bang, into the vast, structured, galaxy-filled cosmos we observe today. For roughly 3 decades, it predicted the large-scale distribution of galaxies with impressive accuracy. It explained the pattern of temperature fluctuations in the cosmic microwave background. It accounted for the observed abundances of light elements. It incorporated dark matter and dark energy in a mathematically consistent way and produced a model of cosmic history that matched observation after observation. Lambda CDM was not just the leading theory. For most working cosmologists, it was the only game in town. After 2 years of James Webb Space Telescope data, Lambda CDM is no longer the theory of everything for the universe. It is, at best, the theory of most things, except the ones that matter most. The wounds have been accumulating in sequence, and listing them together is the only way to feel their full combined weight. The Hubble tension. 2 independent, high-precision measurements of the universe's expansion rate disagree by 9% at 5 sigma statistical significance. And Webb eliminated every systematic error that might have explained it away. Galaxies too massive, too early stellar masses 10 to 100 times larger than all simulations predict, confirmed across multiple instruments and analysis teams. Black holes too large, too soon supermassive objects carrying tens of millions of solar masses appearing before the universe reached 500 million years old, with no known formation pathway that fits the timeline. Cosmic structure too organized, too fast protoclusters and large-scale filaments assembled at epochs when the mathematics of gravitational collapse says the raw material hadn't been gathered yet. And now dark energy apparently not constant. The equation of state parameter W drifting away from -1 across the most precise baryon acoustic oscillation survey ever conducted. 5 separate, independent, mutually reinforcing failures. Not one anomaly that could be a fluke. 5. Into this fractured landscape, a theory that spent decades being dismissed with barely concealed contempt is walking back through the door with new relevance. Modified Newtonian dynamics (MOND), first proposed by physicist Mordechai Milgram in 1983, holds that gravity does not follow Newton's inverse square law at very low accelerations. Below a critical acceleration threshold of approximately 1.2 times 10 to the power of -10 meters per second squared, gravity in the MOND framework becomes stronger than the standard formula predicts, falling off more slowly with distance. This modification was originally proposed to explain the rotation curves of galaxies, the observation that stars at the outer edges of galaxies orbit far faster than Newtonian gravity from the visible mass alone can account for. The same phenomenon that led most astronomers to infer the existence of dark matter halos. For years, MOND was treated as an interesting but ultimately flawed alternative. It could explain individual galaxy rotation curves with surprising accuracy, but it struggled with galaxy clusters and with the large-scale structure of the universe in ways that dark matter handles more naturally. Webb has not overturned that assessment entirely, but it has complicated it. Several analyses of early Webb observations of galaxy morphology and internal kinematics at high redshift have produced results that sit more comfortably within MOND predictions than within standard CDM predictions in specific regimes. The theory has not been vindicated, but it has stopped being easy to dismiss, and serious papers engaging with it on its own terms are appearing in major journals with increasing frequency. Self-interacting dark matter, already introduced in the context of early cosmic structure, carries additional weight in this broader crisis. Standard cold dark matter predicts that dark matter halos should have dense, cuspy cores density, rising steeply toward the center, following a specific mathematical profile called the NFW profile. Observations of dwarf galaxies, low surface brightness galaxies, and galaxy cluster cores consistently find shallower density profiles, cores that are flatter and less concentrated than CDM predicts. This discrepancy, known as the core cusp problem, has persisted for 2 decades. SIDM resolves it elegantly. Dark matter particles scattering off each other redistribute energy within halos, smoothing the central density spike into the observed flatter profiles. Webb's high-resolution observations of early universe galaxy morphology and mass distribution are adding new data points to this problem, and the pressure on the purely collisionless cold dark matter picture is intensifying. Then there is the possibility that cuts deepest of all, the fine structure constant, designated alpha, may not be constant. Alpha is a dimensionless number, approximately 1 divided by 137, that governs the strength of electromagnetic interactions. It determines how strongly charged particles interact with light, how atoms are structured, how chemical bonds form, how spectral lines are positioned. If alpha varied across space or time, the spectral fingerprints of distant atoms would be shifted in ways that go beyond simple redshift. The relative spacings between spectral lines would change. In 2001, John Webb and colleagues at the University of New South Wales published an analysis of quasar absorption spectra, suggesting alpha may have been slightly smaller in the distant past, at a level of roughly a few parts per million. The finding was contested. Counter-analyses using different quasar samples found no variation. The question was never definitively resolved. Webb's spectroscopic capabilities at high redshift are reopening this question with far higher precision than was previously possible. If alpha does vary even at the parts per million level, confirmed across cosmic time, the implications are catastrophic for the Standard Model in a way that dwarfs every other crisis on this list. The constants of nature are embedded throughout the equations of quantum electrodynamics, the Standard Model of particle physics, general relativity, and thermodynamics. A varying alpha does not just require a correction to one equation, it requires acknowledging that the foundational assumption underlying all of modern physics, that the laws of nature are the same everywhere and always, may be false. The scientific community's response to this accumulating crisis is not what popular imagination might expect. There is no panic, no public declarations of defeat. What there is in the seminars and preprint servers and conference rooms where this work is actually happening is something closer to a barely contained exhilaration. Physicists know what moments like this look like historically. They know that the deepest theoretical revolutions do not arrive announced. They arrive disguised as stubborn anomalies, data points that refuse to fit, measurements that keep coming back wrong, numbers that no amount of systematic error hunting can explain away. At the end of the 19th century, physics appeared essentially complete. Maxwell's equations had unified electricity and magnetism. Thermodynamics was mature. Newtonian mechanics worked everywhere it was tested. Then 2 problems refused to go away: the null result of the Michelson-Morley experiment, which found no evidence of the luminiferous ether through which light was supposed to propagate, and the ultraviolet catastrophe, where classical physics predicted that hot objects should radiate infinite energy at short wavelengths. These were small cracks, embarrassing anomalies in an otherwise triumphant edifice. The first crack led to special relativity and then general relativity. The second led to quantum mechanics. Between them, they rebuilt physics from the ground up. The cracks Webb is opening are not smaller. If you were a physicist today, and every new data set your most sensitive instrument delivered contradicted the theory you built your career on, would you adjust the data to fit the theory, or rebuild the theory to fit the data? The current state of cosmology is exactly like the kitchen of a 5-star restaurant, where the head chef has just quietly realized that the secret recipe, the one the entire menu is built around, the one that earned every award on the wall, is missing a fundamental ingredient. The dishes are still going out. The guests are still eating. still praising the food, still leaving 5-star reviews. But in the back, behind the pass, the chef is standing very still, staring at the recipe card, with an expression that the servers have learned not to ask about. But while the theorists patch their equations, Webb is doing something completely different. It is searching for life. And what it found in the atmospheres of distant worlds is about to change the most fundamental question our species has ever asked. James Webb does not only look far, it looks deep. Not deep in the metaphorical sense, deep in the most literal, physical, chemically precise sense possible. It can take the light from a distant star, catch the fraction of that light that filtered through the atmosphere of a planet passing in front of it, spread that light into its component wavelengths with a spectrograph of extraordinary sensitivity, and read the chemical composition of that alien sky like a pharmacist reading a molecular inventory, molecule by molecule, element by element, from hundreds of light years away, without going anywhere near the planet itself. This capability was understood before launch to be one of Webb's most consequential contributions to science. The reality of what it found exceeded even that expectation. K2-18b sits 120 light-years from Earth, orbiting a red dwarf star in the constellation Leo. It is classified as a Hycean world, a theoretical category of exoplanet with a hydrogen-rich atmosphere overlying a global liquid water ocean. First seriously proposed as a potential host environment for life by Cambridge astrophysicist Niku Madhusudan and colleagues. At 8.6 times the mass of Earth, it is larger than our planet, but smaller than Neptune, and it orbits within its star's habitable zone, the range of distances where liquid water can persist on a planetary surface or subsurface given the right atmospheric conditions. In 2023, Webb's near-infrared spectrograph and near-infrared imager and slitless spectrograph instruments analyzed the transmission spectrum of K2-18b's atmosphere during planetary transits and returned a detection that stopped conversations in exoplanet science departments around the world. Carbon dioxide, confirmed. Methane, confirmed. And a signal weak, below the threshold of definitive confirmation, but persistent across multiple observations and analysis methods consistent with dimethyl sulfide. Dimethyl sulfide, DMS, on Earth. This molecule has exactly one known production pathway: biological metabolism. It is generated by marine phytoplankton and other microorganisms as a byproduct of their biochemistry and released into the atmosphere in quantities large enough to be detectable from space. It does not form efficiently through any known abiotic chemical process in conditions relevant to planetary atmospheres. When astronomers and astrobiologists list the molecules they most want to find in an exoplanet's atmosphere as potential biosignatures, chemical indicators of biological activity, DMS is near the top of that list. This is not a confirmation of life on K2-18b. The signal is not yet at the statistical significance required to make that claim, and the researchers who published the 2023 results were careful and explicit about that boundary. There may be abiotic pathways for DMS formation in hydrogen-dominated atmospheres that are not yet fully characterized. Further observations are needed. The science demands caution, and the caution is appropriate. But it is also the first time in human history that a potentially biological molecule has been detected in the atmosphere of a planet outside our solar system. The first time ever. And it was found on Webb's second year of science operations, 40 light-years away in the constellation Aquarius. The TRAPPIST-1 system presents a different kind of target. 7 rocky planets, all orbiting within roughly the distance of Mercury from our own Sun, around a red dwarf star so small and cool that 3 of those planets, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, sit within the habitable zone. These are not gas giants or ice planets. They are Earth-sized, rocky worlds with densities consistent with silicate composition, and, potentially, water. Webb has been systematically working through them, analyzing their thermal emission and transmission spectra where transits permit. The results so far are mixed but scientifically rich. TRAPPIST-1b and TRAPPIST-1c appear to lack thick carbon dioxide atmospheres, constraining but not eliminating habitability scenarios for the outer planets. The inner planet's atmospheric characterization is ongoing. Every transit Webb catches adds another layer of chemical constraint. But the deeper implication of Webb's atmospheric work extends far beyond any individual planet. The broader picture emerging from its observations of early universe chemistry, the same chemical story told by the heavy element abundances in galaxies 400 million to 600 million years after the Big Bang, is that the raw ingredients for biochemistry, the molecular building blocks that on Earth assembled into the first living cells, were being distributed through the cosmos far earlier and far more widely than any pre-Webb model predicted. Carbon, oxygen, the molecular hydrogen and carbon monoxide from which more complex organics form in interstellar clouds. Water, detected in the atmospheres of planets, in the spectra of protoplanetary disks, in the interstellar medium of galaxies billions of light-years away. The universe did not wait until stars had processed matter through many generations before making the chemistry of life available. It started brewing that recipe almost immediately. The significance of this reframing is statistical and philosophical in equal measure. Before Webb, the search for life elsewhere in the universe was haunted by a legitimate uncertainty. Maybe the conditions that allowed chemistry to reach biological complexity on Earth were extraordinarily rare. Maybe the right molecules, the right energy sources, the right planetary environments only coincided here. Webb is systematically dismantling that uncertainty. The ingredients are everywhere. The environments capable of hosting liquid water are numerous. The chemistry that on Earth leads to amino acids and nucleotides, and eventually to cells, is not peculiarly terrestrial. It is a natural output of stellar nucleosynthesis, running through interstellar chemistry, wherever the conditions are even remotely right. Which means the question of life in the universe is no longer whether it could exist anywhere else. It is where, and how far away, and whether any of it has been looking back. Before Webb, searching for life beyond Earth was like trying to find a specific book in a vast, completely dark library. You know books exist. You know the library is large, but without any light, you cannot even confirm the shelves are stocked. Webb just switched on the lights, and the library is immeasurably larger than anyone drew on the architectural plans. So here's the question that earns a genuine pause. If Webb confirms the DMS signal on K2-18b at 5 sigma statistical significance, the same threshold that confirmed the Higgs boson, the same threshold that confirmed gravitational waves, what does the moment of that announcement actually look like for a species that has spent its entire conscious history wondering whether it is alone? The way Webb detects life capturing starlight filtered through an alien atmosphere, decomposing it into wavelengths. Reading the molecular absorption lines like a chemical fingerprint is essentially the cosmic equivalent of standing outside a restaurant, analyzing the smell drifting through the ventilation, and reconstructing the entire menu without ever walking through the door. From 120 light-years away, we may not be alone, but the larger truth is waiting in what comes next, when Webb no longer just maps the boundaries of the known universe, but sketches the outline of the universe that can ever be known. And that boundary is more unsettling than any mystery we have discussed so far. Everything you have ever learned about the universe, every galaxy image, every stellar nursery photograph, every planetary system mapped, every nebula catalogued, every atom studied in every laboratory on Earth accounts for exactly 5% of what actually exists. 5%. The remaining 95% consists of dark matter, which makes up 27% of the total energy content of the cosmos, and dark energy, which accounts for 68%. Neither has ever been directly detected. Neither has a confirmed theoretical identity. Neither can be touched, photographed, or measured in any direct sense by any instrument humanity has ever built. We know dark matter exists because of what gravity does in its presence. We know dark energy exists because of what space does under its influence. Beyond those gravitational and geometric fingerprints, both remain at the level of fundamental understanding, completely unknown. And the crucial distinction here is not that we have not found them yet. It is that we do not currently possess a theoretical framework adequate to describe what they actually are. Dark matter is not like a new element waiting to be synthesized, something that fits naturally into an existing structure and just needs the right equipment to isolate. It is a category of physical reality for which our deepest theories of matter and energy offer no satisfying candidate. The standard model of particle physics, which describes every known particle with extraordinary precision, predicts nothing that behaves the way dark matter must behave. The most popular proposed candidates, weakly interacting massive particles, or WIMPs, have been searched for in underground detectors, at particle colliders, and through indirect astrophysical signatures for 3 decades. They have not been found. Dark energy is, if anything, more baffling. When physicists attempt to calculate its energy density from first principles using quantum field theory, the result is wrong by a factor of 10 to the power of 120. That is not a small miscalculation. That is the largest discrepancy between theory and observation in the history of science. James Webb is the most powerful astronomical observatory ever built. Its gold-coated mirror spans 6.5 meters. Its instruments detect infrared light across wavelengths from 0.6 to 28 micrometers with sensitivity that, on its first deep field image, resolved galaxies that had been invisible to every previous telescope. It can read the chemical composition of an atmosphere 120 light-years away. It can peer back to within a few hundred million years of the Big Bang itself. And it is completely blind to 95% of the universe, because Webb, like every telescope ever constructed, detects electromagnetic radiation light in its various forms. Dark matter emits none. Dark energy is a property of space itself, not a source of photons. The instrument that represents the pinnacle of human observational technology is, by its fundamental operating principle, incapable of directly observing the dominant components of physical reality. We are mapping a continent using only the sounds of birds in a landscape where birds occupy 5% of the territory. The observable universe itself, the sphere of space from which light has had time to reach us across 13.8 billion years of cosmic history, extends 46.5 billion light-years in every direction from Earth. Beyond that cosmological horizon, space continues. How far? The honest answer is that we do not know, and the constraints we can place on it are surprisingly weak. Inflationary models, depending on their parameters, allow the total universe to be anywhere from moderately larger than the observable portion to effectively infinite in extent. The region we can see, the only region we can ever see, regardless of how powerful our instruments become, may be an almost imperceptibly small sample of a vastly larger whole. Every conclusion we draw about the universe's nature, its laws, its uniformity, its ultimate fate, all of it is drawn from this single bounded bubble of accessible light. Our understanding of the cosmos is like that of a blind fish living at the bottom of the ocean, trying to draw a complete map of the sea using only the pressure waves it can feel moving through the water immediately around it. The map is not useless. The pressure waves carry real information. The physics governing them is real. But the fish has no way to know how much of the ocean lies beyond the range of its sensing, what structures exist in the sunlit shallows far above, or whether the ocean it is mapping is the only ocean on the planet. And yet, And this is where scientific humility becomes something more than intellectual modesty. Every crack that Webb has opened in the Standard Model is itself a navigational signal. The Hubble tension is not a failure. It is a compass pointing toward physics that has not been written yet. The impossibly massive early galaxies are not embarrassments. They are arrows indicating where the next theoretical breakthrough needs to go. The anomalous dark matter clustering, the variable dark energy, the premature large-scale structure, the first-generation stellar chemistry. Each one is less a dead end than a precise coordinate on a map whose legend we have not yet learned to read. GPS works by triangulating position from multiple signal sources. Science works the same way. The more precise the anomaly, the more exactly it pins the location of the missing truth. The instruments being built right now are not designed to take prettier pictures of what we already know. They are designed to attack the specific boundaries that Webb has drawn in sharp relief. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will survey the sky in the near-infrared across an area 100 times larger than Webb's field of view in a single pointing, mapping the three-dimensional distribution of roughly 1 billion galaxies to constrain dark energy's equation of state with an order of magnitude more precision than current measurements allow. The Habitable Worlds Observatory, currently in the planning and design phase, targeting a launch in the early 2040s, is being built with a single primary scientific objective to directly image Earth-sized rocky planets in the habitable zones of nearby stars and analyze their atmospheres for biosignatures, for the molecular fingerprints of life. The Lunar Far Side Array, a proposed radio telescope to be constructed on the far side of the Moon, permanently shielded from Earth's radio interference, would detect the 21-centimeter hydrogen emission line from the cosmic dark ages, the period before the first stars ignited, giving us a direct observational window into the epoch that currently sits completely beyond even Webb's reach. So the question that genuinely deserves consideration, if 95% of the universe is invisible to every photon-based instrument humanity has ever built or currently plans to build, what form would a telescope for that 95%, even take gravitational wave detectors, are a beginning. They sense the geometry of space-time rather than its light. And the next generation of space-based gravitational wave observatories, like LISA, will open an entirely new observational band. Neutrino telescopes sample a different messenger particle entirely. But for dark matter and dark energy in their full extent, we do not yet have the conceptual framework to design the instrument, because we do not yet understand the phenomenon well enough to know what signal to look for. Humanity is currently writing confident reviews of a 20-episode cosmic story, having watched only the opening credits of episode 1. But the limit of what we can know is not the end of the story. It is the beginning of the most important one. What comes next in the final act of this journey is not about what we cannot see. It is about what happens when we finally do. Every major crisis in the history of physics has ended the same way. Not with the crisis being explained away, not with the anomalous data being reinterpreted to fit the existing theory, but with the existing theory being replaced by something deeper, stranger, and more powerful than anyone had the conceptual vocabulary to imagine before the crisis forced the issue. This is not optimism. It is the most reliable pattern in the history of science. In 1887, Albert Michelson and Edward Morley conducted what was intended to be a straightforward confirmatory experiment. The prevailing theory held that light, like all waves, required a medium to propagate through the luminiferous ether, a substance permeating all of space. By measuring differences in the speed of light in perpendicular directions as Earth moved through this ether, the experiment was supposed to detect the ether wind. It detected nothing. Absolutely nothing. The speed of light was identical in every direction, regardless of Earth's motion. The result was so clean, so unambiguous, and so incompatible with existing theory that for nearly 2 decades it was mostly treated as a measurement problem, an experimental artifact, something to be explained away. It was not explained away. In 1905, a 26-year-old patent clerk named Albert Einstein took the null result seriously and built a theory around it rather than against it. Special relativity followed. Then general relativity in 1915. The ether crisis did not damage physics. It rebuilt physics from the foundation up. In 1900, physicist Max Planck was trying to solve what seemed like a contained technical problem. Classical thermodynamics predicted that a perfect blackbody radiator should emit infinite energy at short wavelengths, the ultraviolet catastrophe, as it came to be called. The prediction was clearly wrong. Every heated object in every laboratory confirmed it was wrong. But no one could explain why it was wrong within the existing framework. Planck, somewhat reluctantly, introduced the idea that energy could only be emitted in discrete packets quanta as a mathematical trick to make the equations work. He did not fully believe it himself at first. Within a decade, Einstein had used the same idea to explain the photoelectric effect, and the quantum revolution was underway. Quantum mechanics now underlies every semiconductor, every laser, every MRI machine, every transistor on every chip in every device on Earth. In 1998, 2 independent teams studying Type Ia supernovae expected to measure how much the universe's expansion was slowing down under gravity. Instead, both found it was speeding up. The universe was not decelerating, it was accelerating. Something was pushing space apart with increasing force. The teams initially double-checked everything, suspicious of their own results. Both came to the same conclusion. Dark energy entered the scientific vocabulary. The Nobel Prize in Physics followed in 2011. What began as an anomalous data point in supernova brightness measurements ended as the discovery that 68% of the universe is something no one had known existed. The pattern is not subtle. In every case, the crisis was first dismissed as measurement error. In every case, it persisted under scrutiny. In every case, the resolution required not a correction to the existing theory, but a conceptual expansion that made the previous framework look like a special case of something larger. And in every case, the new framework arrived with capabilities and explanatory power that the scientists living through the crisis could not have anticipated. What is different now is the speed. In 1887, it took nearly 2 decades from the Michelson-Morley result to special relativity. The physics community communicated by letter and occasional journal. Ideas moved slowly. Today, a Webb observation published on the preprint server RO at midnight is being read, critiqued, replicated in simulation, and responded to by research groups on 3 continents before the following morning. The 2022 Labe paper on impossibly massive early galaxies generated formal responses, counter-analyses, and follow-up observation proposals within weeks. The machinery of modern science turns faster than at any point in history, which means the gap between crisis and revolution is compressing. Galileo pointed his telescope at Jupiter in January 1610 and saw 4 points of light that moved differently from the stars. He watched them over successive nights and realized they were orbiting Jupiter. Moons, other worlds circling another center. The implications unraveled Aristotelian cosmology over the following decades, not because Galileo forced the conclusion, but because the instrument had simply shown something true that the old framework could not absorb. Webb is doing the same thing at a scale Galileo could not have conceived, not revealing moons around a neighboring planet, but revealing the behavior of galaxies, black holes, dark matter, and the expansion of space itself across 13 billion years of cosmic history, with a precision that the old framework cannot absorb. The theoretical physics community's current state is genuinely unusual. They know the standard model is incomplete. The data is unambiguous on that point now. They know a deeper theory is coming. They do not yet know what it will look like. Which of the competing frameworks will survive contact with the next decade of data? Or which anomaly will turn out to be the thread that unravels the whole tapestry and reveals what lies underneath? And somehow, in that state of structured uncertainty, knowing you are wrong, knowing you are about to be right, not yet knowing what you will be right about the energy in the field is higher than it has been in a generation. So here is the question. History earns the right to ask if the pattern holds. If every previous era of observational crisis produced a theoretical revolution that rewrote the rules, what Nobel Prize-winning theory is currently gestating in the anomalies Webb is delivering, waiting for the right mind to see the shape hidden inside the data? The theoretical physics community right now occupies the strangest possible professional position. They know they are wrong. They know they are about to be right. They do not yet know what they will be right about, and somehow every single one of them is more energized than they have been in years. But before the new theory can be written, the new instruments must be built. And what is being constructed right now will make Webb look like a magnifying glass next to an electron microscope. The Nancy Grace Roman Space Telescope carries a mirror 2.4 meters in diameter, smaller than Webb's 6.5 meters. But paired with a detector array covering a field of view 100 times larger than Webb can capture in a single pointing. Every image Roman takes encompasses a patch of sky that would require Webb 100 separate observations to survey. It is scheduled for launch in 2027, and its primary scientific mission is the large-scale structure of dark energy across cosmic time, mapping the three-dimensional positions of approximately 1 billion galaxies and using baryon acoustic oscillations across that enormous sample to constrain the dark energy equation of state with a precision that the current DESI results, groundbreaking as they are, cannot approach. Where DESI is giving us the first credible hints that W deviates from -1, Roman is designed to measure exactly how it deviates, across what range of cosmic history, and with what functional form. It will not just confirm the crisis, it will characterize the physics causing it. The Habitable Worlds Observatory exists currently as a mission concept endorsed by the 2020 Astronomy and Astrophysics Decadal Survey, the community consensus document that sets priorities for NASA investment across a decade, targeting a launch in the early 2040s. It is designed around a single audacious goal: to directly image rocky planets the size of Earth orbiting in the habitable zones of nearby sun-like stars, and analyze their atmospheric compositions for biosignatures. Not transit spectroscopy, not indirect atmospheric inference from starlight filtering, direct imaging, spatially resolving the planet from its star, capturing its own reflected light and spreading it into a spectrum. If carbon dioxide and methane and water vapor and dimethyl sulfide are present simultaneously in the right proportions, the Habitable Worlds Observatory will see it with a clarity that transforms the question of life elsewhere from a probabilistic argument into a direct empirical measurement. In Europe, the Einstein telescope is moving from proposal toward engineering reality, with a target operational date in the 1930s. It is designed as an underground triangular interferometer with arms 3 times longer than LIGO's, operating at cryogenic temperatures that suppress thermal noise to levels that allow gravitational wave detection, with a sensitivity approximately 100 times greater than current LIGO and Virgo capabilities. Where LIGO hears the final seconds of black hole and neutron star mergers, the Einstein telescope will hear them from across most of the observable universe and will detect signals from sources too quiet for current instruments, including, potentially, the stochastic gravitational wave background from the early universe itself. The gravitational echo of processes occurring in the first fractions of a second after the Big Bang. Webb sees the universe with light. The Einstein telescope will hear it with gravitational waves. These are not redundant capabilities. They are complementary senses, each probing aspects of reality the other cannot reach. CMB-S4, the Stage 4 Cosmic Microwave Background Experiment, is a ground-based observatory being developed as a collaboration between the Department of Energy and NASA, deploying approximately 500,000 superconducting detectors across telescopes at the South Pole and in the Chilean Atacama Desert. Its sensitivity to the polarization of the cosmic microwave background will be sufficient to detect or definitively rule out the primordial gravitational wave signal predicted by inflationary cosmology, directly testing the physics of the universe's first tiny fraction of a second. It will also measure the Hubble constant from the early universe side of the tension with a precision that either resolves the discrepancy or makes its physical reality absolutely undeniable. The Lunar Far-Side Array is the most ambitious concept on this list, and the one that sounds most like science fiction, until you look at the agency proposals already written for it. A radio telescope array constructed on the far side of the Moon, permanently shielded from Earth's radio frequency interference by the entire mass of the Moon itself, would operate in low radio frequencies that are completely inaccessible from Earth's surface due to ionospheric absorption. At those frequencies, it could detect the 21-centimeter hyperfine transition of neutral hydrogen from the cosmic dark ages, the period between recombination and the ignition of the first stars, a span of hundreds of millions of years that no instrument has yet directly observed. The dark ages are, quite literally, dark. No stars, no galaxies, no sources of ultraviolet light to illuminate the hydrogen. Only the faint radio signal of that hydrogen itself, carrying an imprint of the density structure from which all subsequent cosmic architecture assembled. The Lunar Far-Side Array would open a window into the universe's least observed epoch that no Earth-based or Earth-orbit instrument can access. The future of observational cosmology is not a single more powerful telescope. It is an ecosystem, a coordinated network of instruments operating across the full electromagnetic spectrum, supplemented by gravitational wave detectors and eventually by neutrino observatories capable of detecting the cosmic neutrino background from the Big Bang itself. Each instrument addressing questions the others cannot. Each confirmation or contradiction feeding back into the theoretical work, trying to build the framework that replaces Lambda CDM. If you could direct that entire ecosystem toward answering only one question about the universe, one question, completely and definitively, what would you choose? The plan to build a telescope on the dark side of the Moon sounds exactly like a science fiction plot device, and it is precisely what NASA and ESA are currently writing budget proposals for. The new instruments will answer the old questions, but history tells us clearly they will generate far more new ones than they resolve. And the largest question about to emerge is not about galaxies or black holes. It is about us. James Webb is not only a telescope, it is an instrument of relocation, something that picks up the entire human species and sets it down in a different place in its own understanding of where it stands within the cosmos. Every major expansion of the observable universe has done this. Each time the map grew larger, humanity's sense of its own position had to be renegotiated. For most of recorded history, Earth was the center. Then Copernicus moved the center to the sun. Then the sun became one star among hundreds of billions in the Milky Way. Then the Milky Way became one galaxy among hundreds of billions of observable galaxies. Each revision required not just a scientific adjustment, but a psychological one, a reorientation of what it means to be here, in this place, in this moment, made of these atoms, asking these questions. Webb is forcing the next revision, and it is the most disorienting one yet. The anthropic principle, in its most straightforward form, observes that the universe appears fine-tuned for the existence of complexity in life. The physical constants, the strength of gravity, the mass of the electron, the charge of the proton, the energy density of empty space are set to values that, if altered by even fractional amounts in most cases, would produce a universe incapable of forming stars, atoms, chemistry, or anything remotely resembling biological structure. Gravity slightly stronger, and the universe collapses before stars can stabilize. The cosmological constant slightly larger, and space expands so fast that matter never gravitationally clusters into galaxies at all. The fine structure constant slightly different, and carbon cannot form in stellar nucleosynthesis through the triple alpha process, eliminating the chemical foundation of all known life. The numbers are extraordinarily precise, and they are precisely what they need to be. This has always been one of the most philosophically charged observations in all of physics. Some interpret it as evidence of design. Others invoke the anthropic selection effect. We can only observe a universe compatible with our existence. So any universe we find ourselves in must, by definition, have the constants that permit us to be here. Still others point to the multiverse as the natural resolution if an enormous or infinite number of universes exist, each with different physical constants. The existence of at least some with life-permitting values becomes statistically unremarkable. Now Webb is complicating even this, because if the fine structure constant varies across space or time, as some spectroscopic analyses suggest, and Webb is now positioned to test with far greater precision, then the fine-tuning is not a fixed feature of a single universe. It is a local condition, a regional accident. The constants that permitted carbon-based life are not the eternal universal values of physics. They may be the values that had happened to apply in this corner of spacetime, at this epoch, for reasons that have nothing to do with necessity or design, and everything to do with the particular history of a specific bubble of inflation. The anomalies Webb is documenting don't just challenge cosmological models. They are quietly pulling the philosophical rug out from under every interpretation of fine-tuning that has ever been proposed. Webb cannot prove the multiverse. No observation within our observable universe can, by definition, directly confirm the existence of regions outside it. But the accumulating anomalies, the structures too large, the expansion rate too inconsistent, the dark energy apparently in motion, the physical constants potentially variable make the multiverse hypothesis considerably less extravagant than it appeared a decade ago. When the alternative is that a single universe somehow produced all of these inconsistencies by coincidence, a framework in which our observable cosmos is one bubble among vastly many, each with its own physics, starts to look not like speculation, but like the more parsimonious explanation. The psychological journey this forces is without precedent in its scope. From the center of creation to the planet, humanity absorbed that over centuries. From a planet to a star among billions, we had generations to adjust. From one galaxy to one among hundreds of billions, the adjustment happened within living memory of the telescopes that made it visible. But from the observable universe to a bubble, one among perhaps 10 to the power of 500, or infinitely many, each separated from ours by distances that no signal will ever cross. This is a relocation so vast that no previous framework of meaning, scientific or otherwise, was built to accommodate it. In 1990, the Voyager 1 spacecraft, at roughly 6 billion kilometers from Earth, turned its camera back toward the inner solar system at the suggestion of Carl Sagan. The image it returned showed Earth as a point of light less than 1 pixel in size, suspended in a ray of scattered sunlight. Sagan called it the pale blue dot. His commentary on that image that every human who ever lived, every king and peasant, every act of heroism and cruelty, every civilization and its destruction, had occurred on that mote of dust, suspended in a sunbeam, remains one of the most quietly devastating observations ever recorded in the English language. It showed humanity how small Earth is. Webb shows how small everything we can ever know is. The pale blue dot was a photograph of our planet against the solar system. Webb is, in effect, a photograph of our entire observable universe against everything that may exist beyond it. Same structure of revelation, same vertiginous shift in scale. Except now the dot is not a planet. It is the totality of human knowledge, bounded by the cosmological horizon, floating in a reality whose full extent no instrument we can ever build will reach. Knowing that 95% of even this bounded universe is invisible to us, and that this universe itself may be one bubble among effectively infinite others, does that make your life feel smaller? Or does it make the fact of your existence feel more extraordinary? Modern cosmology is doing something that no therapy, no philosophy, no religion has quite managed, making you feel simultaneously as cosmically insignificant as a single atom in the Pacific Ocean, and as astonishing as the fact that atoms somehow became capable of comprehending oceans. And in all the mysteries Webb has opened, there is one thing it has made clearer than ever before. We are not the audience of the universe. We are part of the experiment. But what rules is that experiment running on? We do not observe the universe from outside it. There is no outside. We are the universe observing itself, matter and energy, that assembled over 13.8 billion years into structures complex enough to build instruments, ask questions, and look back across cosmic time at the conditions that produced them. This is not poetry. It is the most literal physical description of what is happening when a human being looks through a telescope. The carbon in your body was forged in the triple alpha nuclear fusion process inside the cores of stars at least 1 to 3 times the mass of our Sun, during the red giant phase of their evolution, at temperatures exceeding 100 million Kelvin. The oxygen you are breathing right now was synthesized in stellar cores through the fusion of carbon and helium nuclei, then scattered across space when those stars shed their outer envelopes or exploded as supernovae. The nitrogen in your DNA was produced in similar stellar processes. The iron in your blood was forged in the cores of massive stars and violently expelled in supernova explosions, the most energetic events in the universe short of the Big Bang itself. Events powerful enough to briefly outshine entire galaxies of hundreds of billions of stars. Every atom in your body, heavier than hydrogen and helium, was manufactured inside a star that died before our solar system formed. And every one of those atoms traveled through interstellar space before being incorporated into the molecular cloud that collapsed 4.6 billion years ago to become the Sun and its planets. And eventually, you, the elements that Webb is detecting in galaxies 12 billion light-years away, the carbon absorption lines, the oxygen emission signatures, the silicon features in the spectra of ancient stellar populations are the same elements, forged by the same processes, that are at this moment forming the neurons reading these words. The universe that Webb is photographing is not something separate from the photographer. It is the same continuous physical system, observed from one particular location within itself, at one particular moment in its own evolution. We are living through an extraordinary moment in the history of cognitive life in this cosmos. For almost all of the 13.8 billion years since the Big Bang, the universe has existed without anything in it capable of asking why. Stars formed and died in silence. Galaxies collided without witness. Black holes consumed matter with no observer to record the event. The entire first 12 or 13 billion years of cosmic history unfolded without a single mind anywhere in the observable universe capable of modeling it, questioning it, or building mathematics adequate to describe it. Then, in a cosmic eye blink, on one unremarkable rocky planet, orbiting one unremarkable star in the outer arm of one unremarkable Spiral galaxy. Biological evolution produced nervous systems complex enough to do something the universe had never managed before: represent itself. First in fear, looking up at stars and seeing gods. Then in curiosity, naming the constellations, tracking planetary motion, building the first crude models of celestial mechanics. Then in systematic inquiry, Copernicus, Galileo, Newton, Einstein, Hubble, each extending the reach of the model, each pushing the boundary of what the universe could know about itself. And now, finally, this a 6.5-meter mirror in space, beyond the distorting blur of Earth's atmosphere, looking back to within a few 100 million years of the Big Bang, seeing galaxies that should not exist, measuring a universe expanding at a rate it cannot explain, finding the molecular signature of possible biology on a world 120 light-years away. This is the endpoint so far of a process that began when the first living cell divided in ancient ocean water. The arc from single-celled organism to James Webb Space Telescope is not a straight line. It is not inevitable. It required conditions, timings, catastrophes survived, extinctions that cleared ecological space for new complexity. But it happened. And the result is that the universe, for the first time in its history, has a part of itself that can look at the whole and ask, what are you? And how did you begin? Scientific wonder is not a weakness dressed up as intellectual virtue. It is the cognitive state that drives every act of sustained inquiry, the refusal to accept that a mystery is just a mystery, the insistence on pressing deeper, the willingness to rebuild every framework that stops working. The history of physics is the history of wonder refusing to settle. Every equation that describes reality started as someone refusing to stop being astonished by something they could not explain. So when you look up at the night sky tonight, knowing that the atoms in your eyes were forged in stellar cores, knowing that the light hitting your retinas left some of those stars before Earth existed, knowing that somewhere in the photons arriving from distant galaxies are echoes of processes that Webb is now decoding into a story of how everything began. Does that change what you see? Humanity is how the universe asks questions about itself. And based on the rate at which Webb is delivering answers that generate 10 new questions each, the universe appears to be profoundly confused about its own nature. We are the universe asking. But the final answer, the one this entire journey has been building toward, is not what you think, and it is not inside any telescope. Throughout this entire journey, we have cataloged the fractures: galaxies too massive for their age, black holes too large for their timeline, dark matter clustering faster than quantum mechanics permits, dark energy apparently drifting from its assigned constant, the expansion rate disagreeing with itself at 5 sigma confidence, structures too enormous for the universe to have built within inflationary bounds, chemical enrichment too advanced for the time available. Every single one of these anomalies, documented, confirmed, and resistant to every systematic error explanation thrown at them. Now comes the part that reframes all of it. Every anomaly described in this story, every impossible galaxy, every premature black hole, every structural violation, every measurement that refuses to fit exists within the observable universe. That sphere of space, 46.5 billion light-years in radius, bounded by the cosmological horizon beyond which no light has had time to reach us. We have been treating this bounded bubble as though it were the whole, as though the rules we derive from studying it must be the rules of everything, as though the physics that governs the 5% of it we can directly observe must be the physics of all reality. According to the best supported models of inflationary cosmology, currently available frameworks that have passed the most rigorous observational tests we have applied to them, predicting the spectrum of cosmic microwave background fluctuations with extraordinary accuracy. The total extent of physical reality is at minimum 10 to the power of 23 times larger than the observable universe. That number does not have a name in human language. It is not a trillion, not a quadrillion, not a Google. It is 10 followed by 23 zeros times the size of everything Webb can see. Everything any telescope we will ever build can see. Everything that has ever been or will ever be accessible to any measurement made from this location in space-time. 10 to the power of 23. The observable universe, all 93 billion light-years of it, all the galaxies and voids and filaments and everything Webb has been photographing is, relative to the total physical extent of reality that inflationary cosmology implies, smaller than a single atom, is relative to the observable universe itself. We have been deriving the laws of nature from a sample so vanishingly small relative to the whole that the word sample is almost too generous. In this context, the anomalies Webb found are not the unsettling part. The unsettling part is the question they force. We have been asking, why does our universe behave in ways our models cannot explain? But the more precise question is, why did we assume that the rules governing our particular bubble of post-inflationary spacetime should be universal laws, applicable everywhere and always, derivable from observation of this one small region? There is a feature in the cosmic microwave background that has resisted comfortable explanation since it was first clearly mapped by the WMAP satellite and confirmed by Planck. The cold spot, a region in the southern sky, roughly 1.8 billion light-years across, significantly colder than the surrounding microwave background, whose temperature deficit and internal structure do not match the statistical predictions of standard inflation. Various explanations have been proposed: a supervoid in the large-scale structure along the line of sight, a statistical fluctuation at the tail of the probability distribution, a topological artifact. None has been fully satisfying. One explanation that has not been ruled out, and that remains, in the language of theoretical cosmology, a live hypothesis, is that the cold spot is a bruise, a collision imprint, the gravitational and thermal scar left on our cosmic microwave background from the epoch of inflation, when our bubble of space-time was not yet fully separated from a neighboring bubble, another universe, running on its own physical parameters, briefly pressing against ours before the inflationary expansion drove them permanently apart. This is not confirmed. The available data is consistent with it, but not uniquely explained by it. It is, however, the kind of hypothesis that was until recently dismissed as untestable metaphysics and is now being written about in peer-reviewed journals as a legitimate empirical possibility because the anomaly it proposes to explain is real, persistent, and unresolved by any mundane mechanism. The cosmological principle told us that our location is not special. Lambda CDM told us the rules are universal. The anthropic principle asked why the constants are fine-tuned for life. All three frameworks share a single hidden assumption that the universe we can observe is representative of the whole. Webb has spent 2 years delivering evidence that something is wrong with our models of this observable universe. But the deeper possibility, the one that contextualizes all of it, is that our models were never going to be fully correct because they were built from a sample of reality so small that local conditions, local histories, local fluctuations in physical parameters may have been mistaken for fundamental laws. James Webb is looking at the edge of our light bubble. Everything it finds that shocks us, every galaxy that should not exist, every measurement that does not close all of it, may be the echo of physics happening outside, in the regions beyond the horizon, where no signal will ever reach us, where the rules may be different in ways we have no framework to describe, and no instrument that will ever detect. The James Webb Space Telescope is not showing us the universe. It is showing us for the first time, with clarity too sharp to deny, that what we call the universe is only the part that light reached in time, and the part that light did not reach, no one knows what it is, how large it is, or how many there are.